Good afternoon, everyone. Quick administrative reminders. Homework 3 has been posted. Same deal, I'm sure you guys are all used to now. It'll be due next Wednesday. And then in addition to that, project proposals will be due on Friday. I've gotten some feedback, either talking to you guys directly or through email about the project proposals. There might be one or two that I haven't responded to yet. So if you're waiting on me, I will get around to that. But for folks who haven't reached out, please make sure just to have a quick check-in before you submit the proposals. Okay. So today we are going to talk about some more classification algorithms. And last class we left off with logistic regressions and multinomial logistic regressions. And before we kind of cap off that topic, I did want to talk about one particular nuance with logistic regressions that is oftentimes important to know in practical applications. We don't cover obviously as much in theory, which this kind of stems from, but this concept that we'll be talking about is also important to think about sort of directly in modeling applications as well. So one of the central tenets of logistic regressions is that you have something known as the independence of irrelevant. Sorry, let me rewrite that. Irrelevant alternatives. This is known as IIA. And this means that adding another option or changing an alternative option does not affect the relative odds between the options considered. Okay, and this sort of particular assumption having to do with the way that logistic regressions work, I think is kind of nicely demonstrated in this example. I actually don't know who came up with this example, but it's like taught in all the classes now, called the red bus blue bus problem. So red bus, blue bus problem. It happens to line up with transportation, which is kind of nice. So let's say that you commute to work every day and you have a 50% chance of commuting with your car, and you have a 50% chance of commuting with a bus. So let's now suppose a new mode is added Okay, and let's actually say the color of this bus is the color of the original bus is red. And the new mode that's added is a blue bus. Blue bus. Okay, so let's say commuters don't care about the color of the bus they ride. That would then mean that you should have something like probability of red bus is equal to the probability of the blue bus. Okay. So that's fairly straightforward, right? And makes sense, right? Like most people don't really care about what what's painted on the side of the bus or the color of the bus. It's not like a blue bus comes by to the bus station and you're like, oh no, I'm not going to get on this bus because it's blue. I'm going to wait for the red bus. They're exactly the same. And so you might think that then the probability of the car equals 0.5, and then the probability of the red bus would be equal to 0.25, and probability of the blue bus would be 0.25. And so here is where the kicker is. So IIA doesn't let us do this because the relative odds must stay the same. Therefore, the probability of the car is equal to the probability of the red bus equals the probability of the blue bus. So that's going to end up being 0.33. Okay, and so why is this? Remember that in the logistic regression, you have this kind of thing where you have your beta x for your particular outcome, let's say J, right? So probability of your particular J outcome is equal to this divided by the sum of EXP for all of the other options or choices, right? And so your ratio between your beta J x and any other individual beta, let's say beta I x, because those betas don't change, the ratio between the probabilities have to be relatively the same. And so because the probability of the car and the probability of the red bus were initially the same, as you add in more options, because they're all independent, then they have to stay the same. So you couldn't have a situation where suddenly the car is twice as likely as the red bus. Okay. And so the implications of this are that you're assuming independence in the choices. And there are ways in which you can modify this particular model, which is commonly done because of this particular issue. You may have heard of things like nested logit, or even mixed logit, which these both help to relax the IIA restriction in this model. We won't get into that. That'll be for folks who are, particularly interested in kind of discrete choice models. You can take sort of more advanced courses that delve a lot more into the theory and detail behind this. But for general awareness, this is something that you guys should be at least somewhat knowledgeable about. So yeah, one of the weird sort of artifacts of the way the model is set up is that you have this assumption of independence that leads to the relative odds between two choices always having to be the same. Okay. So moving on from logistic regression, we are going to, like I mentioned at the beginning of class, talk about a couple other classifier algorithms. But before we talk about the next one, which is going to be it's known as a linear discriminant analysis, it's actually related to a concept known as dimension reduction, which isn't something that we've talked about before. So I'm going to introduce this topic first, and then we're going to go back in the latter half of class to talk about these other classifier examples. And so when I talk about dimension reduction, we're actually going to go back in time a little bit and revisit an older topic for selection and regularization. So selection and regularization. So if you guys remember, this is all about figuring out sort of what's the best model given some choice of parameters, or some choice of variables. So we talked about subset selection. So this is forwards/backwards stepwise selection. Okay. And kind of the principal idea here is that we are reducing the number of coefficients, right? We are essentially filtering out certain combinations of coefficients, certain number of variables, so that we can deal with a sort of smaller subset, and it's easier to parse, right? We also talked about shrinkage. So this is our ridge and lasso regressions. And this shrinks the coefficients. And the whole point here, it's in principle kind of similar to subset selection in that you're essentially getting rid of the influence of unimportant coefficients. And so the last one that we'll talk about is known as dimension reduction. So this is this would be something like principal components analysis, which we'll talk about. This is PCA. And the whole idea is this will transform and combine predictors. Okay, so let's go ahead and think about talk about how this works in theory. So let's revisit our linear equation. We'll say beta 1 x1 plus beta 2 x2 all the way on to beta k xk. So in dimension reduction, so I'll kind of write out a couple equations and then we'll talk about essentially what's going on and qualitatively sort of how they work. I'm going to have a different set of linear equations where I can do something like this. Okay, so this equation looks an awful lot like just your typical sort of linear regression type of equation. And you are essentially combining your x's through some other parameter. So in this case, we have this, oh, I forget what this Greek symbol is. Whatever this Greek symbol is, I'm blanking on it. That parameter is kind of like the betas that you see in the linear model. And you've got linear combinations that transform x to z. And most importantly, m is less than k. And the whole idea here is that I want to be able to reduce, I essentially want to be able to reduce the number of variables and your input parameters to a smaller quantity that's a little bit sort of more digestible. And you're doing this in such a way that you are getting, that your linear combinations are trying to extract the sort of most important explanatory power out of all of the variables that you have in your sort of initial model. And so we'll talk about sort of what that means in a moment. And I'll show you this particular example of the principal components analysis where the way they kind of constrain these parameters in your dimension reduction to be kind of circles in each dimension. And so again, I'll show you what this means in just a second. So this would be your sort of PCA. And so what this ultimately does is it will transform, it's theta. I just remembered, yeah, theta. So it's going to transform your linear regressions into this set of thetas. Oh. Different set for this one. Okay.
Hi, just a quick question. So that epsilon at the end is outside of the summation, right?
Yeah, yep, that's right. It should be like this. All right, so the question is kind of what's going on here. Let's say we've got a couple variables. So we're going to look at x1 and x2, and you've got kind of a bunch of data points that might look something like this. So I want to be able to essentially look at something like this, where I'm going to build a so in this principal components analysis, you are breaking down and doing this linear combination of multiple variables into the components in which they are contributing to as sort of explanatory power for your response variable. And so the first component is going to be the one that sort of maximizes variance. So you want to take it in the sort of longest direction possible. So this would be our first component. And then dimensionally, all the components are meant to be independent. And so your next component in this particular example, so they would always need to be orthogonal or perpendicular to your first component. So the place where this kind of oval is widest would be my second component. It would look something like this. It's a little bit like less interesting, I guess, when we are drawing this in 2D, because you're kind of talking about going from two variables into two components, and so you're not really reducing the dimension much. But you can imagine how this kind of process can extend outwards into many different dimensions. And I can essentially do this process where I sort of draw this bubble, figure out where the maximum variance is, look at the longest length, and then use that as a component. You can imagine that as I go through more and more components in a system that may have many dimensions, that at a certain point, like I don't, like the explanatory power of adding more components becomes less and less important. And so this is this whole idea of getting back to the concept of like overfitting. You could have a million variables, and in the old examples, you could do forward or backward selection and start filtering out some of those variables, or you could do shrinkage and then make a whole bunch of those variables coefficients like shrink down to 0. Or you could do this dimension reduction, which is probably the most powerful method for dealing with large quantities parameters, because it enables you to capture the like best contribution of each variable to your response. And so you can see, like, if I were to draw a slightly different example, x1, x2, let's say the points are like way more kind of spread out. And my circle kind of looks like this. You know, your first component might still be here, but then your second component might look something like this. So first component, second component. So on the example on the left, you can see that the first component is going to be kind of relatively more important than the second component. But in the example on the right, they're going to be much closer in sort of importance, right? And so the z's and the z's, which represent the components, are going to be all independent from each other. And since you're selecting m less than k, always select less than k, we reduce number of dimensions and prevent overfitting. And so similar to the way we select the number of regressors in a stepwise selection, similar to the way that we select lambda for your ridge or lasso regressions, the number of components that you choose to select for your PCA can be determined by metrics that will say you're doing the best job for things like out of sample prediction. So again, like things like cross validation would be a good way to determine, right, how many components to include in the PCA. Okay, any questions about this? Okay, we can jump on over to our studio and show an example implementation of this. Okay. Let me load in a couple libraries. And then we're going to look at a data set from ISLR, a different one. Is the data set called hitters. So let's take a look at this. Okay, hang on. This is a data set of baseball players, and it gives some stats about individual players, RBIs, walks, the league that they're in, the division that they're in, putouts, assists, errors, salary. And the first thing I'm going to do is actually I'm just going to get rid of all of the incomplete cases. Anything with NAs, I'll just go ahead and drop. And what we can do is do so principal components regression analysis, PCR fit, which we use with the function PCR. And generally, right, the way that we feed in the data for PCR, it's the same way. And for these types of things, it's typically a good idea to give it as much information as possible, right? Because we're talking about doing this dimension reduction. So unlike, something like a stepwise regression where you're limiting the variables that go in, here you usually want to just put all of the data that you can. And then it's just going to do its best job at what's going on here. It'll do its best job at taking the most important components of each variable that contribute to the response. And in this case, I can explicitly specify the cross-validation procedure as a way of choosing the number of components. Oop. One second. Oh, I didn't load the package. Give me one moment to find which package I need. I think it's PLS, which I don't have installed for some reason. Okay, yes, it is PC. So PLS is the package that contains the PCR function. Okay, let's take a look at the summary for PCR. Okay. This is going to be slightly different. This gives us some diagnostics about the cross-validation root mean squared error values across a number of different components. And so usually you're going to want to be looking at the for the model that has the lowest root mean squared error. And that tells you something about which is the sort of best number of components to use. So in this case, it looks like 6 or 7 components tend to have kind of the lowest, although it looks like 18 gets there as well, which is even a little bit lower, although that in that case, you're close to having all of the components, and you might be worried about some overfitting. And so, you know, that can play into your sort of decision making here. But I would say sort of more importantly, when you're thinking about kind of looking at the summary statistics for the model results, you're going to notice that like the diagnostics that it's telling you about isn't all that useful for interpretation. Okay, I see a question in the chat. So is the number of components equal to m? Yeah, that's exactly right. So you're deciding how many m's or how many components there you should include in the model. You could actually go back and get the values of those thetas, but that doesn't really tell you anything, right? In terms of like the interpretation, you know, when we talk about interpretation for a beta, we're kind of saying as X changes by so-and-so amount, then Y changes by so-and-so amount. But that is not what, you wouldn't be able to extract anything from the thetas in the principal components analysis, because they're getting these little pieces of contribution from all of your variables. So in that sense, from an interpretation, like results interpretation standpoint, your coefficients in a PCA or your PCR are basically meaningless. And so this type of model you can employ as a way of doing predictions, right? So it's given some values of all of the variables, I could go back in, predict new values, and use the dimension reduced model to predict what my outcome would be. And so this is kind of our first example of a regression approach that is entirely sort of only useful for predictive purposes and totally useless for inference purposes. Whereas most of the previous things that we've talked about, you have a little bit of both, right? Where you're able to do predictions, but you're also able to do inference. And so we can take a look at the validation plot. So this is what happens to your mean squared error as you increase the number of components. And you end up getting a little bit of sort of up and down variance and noise. That's fairly common to see when you're running these types of models. But the thing that you'll immediately notice is that even as you start to add specific components, even after this sort of first component, you should be seeing the sort of biggest drops in that the addition of more components, all of the decrease in your error should be sort of marginal, or at least in theory should usually be smaller in contribution than the last component, because you are specifically going at them one at a time to pick the ones that have the sort of biggest contribution. So I believe that the built-in version uses like a version of a sort of in-sample cross-validation. And so if I wanted to do some out of sample validation, I can do something like this. So I'm just gonna copy and paste this over. So this is out sample validation for selecting number of components. I'm going to divide the data into training versus testing data. In this case, unlike the k-fold ones, this is kind of a k-fold, but it's a value of 2. I'm just splitting the data randomly in half. So I'm sampling true or false from number of hitters, which just means that for each row, it's going to pick it or not. And then testing is everything that's not going to be in the training. And so you can use this option called subset in the PCR as the subset of data that you want to train on, and then it'll test the cross-validation specifically against the out-of-sample stuff. And so I can run this again, and then we can look at the validation plot once again to see. And actually in this case, once you start, once you do cross-validation without a sample, this makes a lot more sense, where you start to see this upward trend in your mean squared error directly as a result of overfitting as you add more components. And so now we've done it sort of in a proper way that actually penalizes you for adding more components, because we get to observe the overfitting when we predict against the out of sample data. Okay. So why don't we, so that's kind of our summary for principal components analysis and how that's kind of applied in regression. Let's take a 5-minute break here before we sort of move on back to our classifier examples. Yeah, and in the meantime, if anyone has any questions, if any of this is confusing, yeah, just let me know and we can chat more about it.
I have a question about the validation that is default in this PCR.
Yep.
How is that an in-sample cross-validation? How is that working? Is it like it operates on all the data and then just use part of it to do the validation?
Yeah, it validates against itself. So you train the model and then it'll do some kind of cross-validation where it's just selecting data that you've trained the model on. So it's in-sample validation as opposed to out-of-sample. So you tend to do a lot better with in-sample. Yeah. So the way you'd imagine is like you run it, you get the results of your PCR, and then you simply take randomly selected data from your hitters data set and you do a prediction of it, and then you compare against the actual data points and get your mean squared error. So it's exactly the same as out of sample, except it's data that you've trained on.
Oh, okay. But in the results, in the summary, there's still like the training and testing part.
Yeah. So this just means that the data that you've trained on, so it doesn't actually say anything about out of sample, right?
Yeah.
So it's just of the data you trained on, how much variance is explained by the model.
Okay, so the difference is actually like in the training, it's all the data you use, and then in the validation, it's just part of it.
Yeah, and so you should see that in this one, that once you have all the components, you should be able to capture all of the variation because you literally have one set of components being explained for every dimension. So you get 100% of the variance. But in the out of sample one, okay. you would still get yeah, I guess you would still get 100% of the variance because you're still getting to no degrees of freedom. So but generally in the out of sample one, is this right? Your root mean squared error should be higher, although I'm not exactly sure how if these are analogous, because it depends on which ones that you it depends on which values that you're actually comparing in the cross validation and how you do the mean. So yeah, I don't think you can actually directly compare these ones.
Okay.
Yeah.
I have a quick question.
Mm-hmm.
Can we use like this PCR function to model categorical variables?
Yes, it'll just treat them as dummy variables. Wait, hang on. Categorical variables in your explanatory variables, not in your response variable. And we'll talk about, actually the next classifier kind of employs this kind of a sort of analogous type of technique for linear combination. So in fact, in this model, like hitters, I believe has some categorical variables. Yeah, it does. So you have like league and division. So those end up just getting treated as dummies. And that's okay, right? To have, because it's just like ones and zeros. And the dimensional reduction of that is, if anything, probably easier.
But for like our y variables, is there like analogous?
Yeah.
Here, okay.
Yeah. So so like we do PCR for continuous y's, and then we're actually going to talk about a somewhat analogous version of PCR for categorical y variables. So I actually, we're 5 minutes into our break, so we'll even get started right now. The whole idea is that we're going to look at this thing called linear discriminant analysis. And so linear discriminant analysis, LDA, is to a logistic regression kind of like what a PCR would be for a linear regression. Kind of. Okay. So let's jump back to the whiteboard to talk about this. So other classification examples. So linear discriminant analysis. So the way that this kind of works is kind of in reverse of of your logistic regression. And what that means is that in a logistic regression, generally you have you're modeling the conditional distribution of your y outcomes given your x's. So you basically say, I'm going to look at all the distributions of my x's and figure out what the sort of corresponding probability of your y outcome looks like, that probability distribution. In an LDA, it's kind of the reverse. So we're going to look, so in theory, the way it works is that you are examining the distribution of x for all of the observations under each specific response class. So, okay, just to maybe I'll sketch like an example. So like if you're if your distribution of x's look like this in totality, what we're actually going to do is break this down. So x1 given y. So let's say your y has two outcomes. You have you have y 1 and you have y2. So you may actually have something that looks like this. And you can imagine a similar thing for your x2s. And so we're going to look at the distribution of your x's for every response class, and then we can use Bayes' theorem as a sort of way of reverse calculating the estimates for y given your x's. So the opposite of what the logistic regression is doing. Clear all this out. Okay, and so, we're talking about kind of the same thing in the sense that we're still going to be estimating these predictors for how your outcome may change given your x's. And so why would we do LDA as opposed to just a logistic regression? So this tends to work or works better for well-separated classes. So in that example that I gave, where you have this like bimodal distribution, if they like cleanly break apart, that's oftentimes a sign that that an LDA will typically perform pretty nicely. If predictors are normally distributed, then this is more stable than logistic regression. And lastly, it's popular when more than 2 response classes. Okay. So let's get down to some of the math behind it, which again isn't something that you'll really kind of need to know in any great detail. You don't need to like memorize this or anything, but as I was mentioning before, it's grounded in Bayes' theorem, which is the probability the probability of a particular outcome K given your X observations is something like this. So this is your probability of outcome K, and this is density function of X for an observation from K. So if you had this information sort of in aggregate, you can figure out the specific probability for one particular observation X that it would belong to a particular response. So your K. But the problem here is that we don't know anything about the density function of X for one observation, right? Because it's a singular. So, okay, so we don't know what Fk of X is. Therefore, LDA assumes Fk of X is just like this. Okay, and this is, all this means is that the fundamental assumption that the LDA model makes is that this Fk of X density function is distributed normally, and that's it. And that's why it's talking about how when the LDA is particularly suited for fitting to data where the predictors are normally distributed, because that's the kind of fundamental assumption. And if you take this assumption and you plug it into Bayes' theorem and you solve all the math, you end up getting an equation that looks like this. And so this is your sort of typical LDA equation. And again, not something that you need to memorize, but the whole point of this is that this value here, this represents assignment of observation to class K, for which delta kx is largest. Okay, so what the heck is going on here? This just means this delta is essentially like the probability. And if you take in your values and you, for any particular observation, set of observations for that particular class response, you can plug them into this equation, and whichever delta ends up being the highest is like the likeliest chance that that's the outcome. And in fact, most LDA models just say that that would be the predicted outcome. So this classification method is kind of a, uses sort of fundamentally different techniques and approaches to do this classification scheme to look at observations and calculate the probability that they belong to a particular response class for your outcome variable. Okay, so let's, unless there's any questions about that, let's jump back over to R and show an implementation of this technique. Okay, example of linear discriminant analysis classification fitting the LDA model. We'll have a different one, LDA fits. Actually, one moment. I need to grab the data set of interest again. So this is that car seats method, or car seats data set that we used in the previous lecture, looking at shelf locations as a function of specific variables. We're looking at prices and sales. And I'll go ahead. So this is directly from the last. This is directly from the last lecture where we came up with a table of values for our predictors so that we could predict a new set of outcomes with the multinomial logistic regression model. And in this case, we're going to do the same thing, but with the LDA model. So LDA.fit, we're going to look at the same model as the multinomial logistic regression that we did before. Oops. Oh, lots of typos, sorry. Okay, so we've got that. Let's take a quick look at the summary just to see if it tells us anything useful. Not too much, but what you can see are some of the values that we would be getting in the parameters for the equation, such as the means, the standard deviations, the number of levels. And because it's based off of Bayes' theorem, it can also tell you the priors for the model. But probably more interesting, and again, this is more for, I think, predictive purposes than inference purposes. So we're going to do prediction across our range of prices and sales. So I'm going to create a new column in this table called the shelf lock LDA, and it's going to do a prediction. The dollar class tells me, because the predict is actually going to give you the probabilities, the dollar class will give you which class in the response that each prediction belongs to. So that will look something like this. So hopefully, if you recall from last class, these are particular outcomes, and you can actually see that the LDA actually looks fairly similar to the logistic regression model. It's going to be linear in the bounds because of the way that we structure parameters for these. They're both still linear and parameter models. And you can see how well it's doing its predictions. And sort of to rehash what I was mentioning at the end of class last time, we haven't talked about, and we probably won't talk too much about this, about the metrics with which we decide to do like model selection. So similar to stepwise regression, for example, the analog in here, in the linear regression, we were using things like adjusted R squared, AIC, BIC, and then obviously the out of sample mean squared error. And as I was mentioning before, with these types of models, the type of error rate that you'd use for like a mean squared error analog would be how often you're getting your prediction correct for classification. And you could do the total one, and you could compare like the logistic regression model versus the LDA and see which one does better. Or you could look at, a type 1 error or a type 2 error, and in that case, you may prefer a particular type of model. So and/or particular set of variables to include in the model. And so again, like, think about what it is that you're trying to do with the model, what sort of classification outcome that you really want, right? Whether or not it's the total error or it's a specific type of error, and then use that as the basis for both selecting the type of model, but also selecting the type of parameters to put into the model. Okay. Any questions about LDA before we move on?
I have a quick question.
Yep.
Like, is in the graph, is the shelves lock.IDA, is that the shading, or is that?
Oh yeah. Oh, okay. Sorry. I should probably explain this a little bit more. Yeah. So this is analogous to before. Let me just pull it up so that we can see. It's probably gonna look pretty similar, but so we'll do a couple spaces here. So this is from last class. So this is the multinomial logistic model. And what you're seeing here is So there are a bunch of dots with black circles, and those represent real data. And those actually represent the data points on which we calibrated this model. I don't know why some of this stuff is not showing up. Hang on. Let's do that. Yeah, here we go. Okay, so each of the points are actually individual data points in the data set. And then it's a little hard to see, but I've done a prediction across a really wide variety of points just to kind of shade it in. So the actual ones, and then this dot logit means the predicted ones, which are all the ones in the background. Okay. And so my prediction, if I'm at this price and at like 15 sales, is that the car seat is going to be located on a good shelf location. If I go over to sales of 5 and a price of 150, my model is going to predict that it's in a medium good shelf location in blue. And so this is, what's it called? It's the domain, it's the like prediction domain of a particular outcome. And then you can see how well the model does based off of, you know, how many red points are in the red, how many blue points are in the blue, and how many green points are in the green compared to the total. And that would be like your total error rate, which would be kind of analogous to using a mean squared error in the sort of continuous response variable types of models that we've seen so far. Does that make sense?
Yeah, that makes sense. I was just getting confused because I couldn't place where the light colors were, but
yeah,
on each other.
Exactly. Yeah, so there's just so many of the light colored ones. And then, oh, what happened to this? Let's see. It's because I overwrote the cars.name. Okay. Yeah, so all the light colored points are all the stuff in the back. So you can see the LDA compared to the logit actually looks pretty similar. I think the like slope was like slightly higher. But now we're actually going to talk about a different classification method that uses a very, very different approach than either of these two, and we'll actually show some nonlinearity in its boundaries, which is actually a good segue for us to start talking about like semi-parametric and non-parametric models, which we'll start into, I believe we'll start into next class. So let's talk about the final classifier. Oops. All right, let's talk about K nearest neighbors, also known as KNN. Okay, I'm gonna just write out the equation, which honestly is just strictly for reference. I think that there's much better ways to kind of understand what's going on here than looking at this equation. Okay. So the idea here is that, so given a positive integer k and a test observation x0, you identify the k points closest to x0, which is represented by n naught. this equation will estimate the probability for class J as the fraction of points in your N0 whose response equals that value, equals J, essentially. So it's a classification of X0 to the class with the largest probability. That's like the formal definition of this equation, but it's actually really simple to understand. Let's do this. We'll just draw a whole bunch of points. I'm gonna go ahead and put a triangle right there. So let's say this is our X0. This is a observation that we want to do a prediction on. Is triangle, or okay, let's say, does triangle belong to X or circle? Red or blue? Okay. At k equals 1. What does this mean? It means I want to look at my nearest, at my one nearest neighbor. Okay, well that's gonna be this guy. So at k equals 1, triangle equals blue, and that's it. Because I classify my point to as according to the quantity of its nearest neighbors. Okay, what about at k equals 2? So I'm going to say my two closest points are here, and let's say here. So in this case, we actually have a tie. And so I will just use the last value, which also represents like distance, right? Because we're looking at the closest one, it's more like the last one than it is like the X, because it's closer to the circle in the case of a tie. Okay, what about at k equals 3? Well, those are my first two closest, and I'm going to say the next closest to me is this guy. So at k equals 3, I would classify the point as a red X. Okay, so this is the principle of k nearest neighbors. You just look at the closest points to you, and you figure out what class they belong to, and the one with the most elements in that class will be the sort of winning classifier. It's going to be the highest probability, essentially. Yeah, so hopefully that yeah, go ahead. I think
So
here's
question,
some.
would it matter at all if for the k equal to 3 case if the red X's were really like much farther away than the blue one?
Yeah, definitely. So we could, let's just say hypothetically that instead of putting the triangle there, I put the triangle here. Then possibly these guys are going to be closer than those X's. And so at k equals 3, it would be blue circle. So you're always looking at the ones closest to it. You can just get a direct sort of point out to the closest neighbor. and then you just count them. So let me then pose a hypothetical question here. 8, 9, let me just see. Yeah. 13, okay. Dot, dot, dot. At k equals 19. Okay, I'm gonna put a triangle here, 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 here. Who can tell me at k equals 19 what each of these triangles are going to be equal to? Is it going to be blue? Is it going to be red? Which ones are going to be blue? Which ones are going to be red? Anyone want to volunteer?
Are they all going to be blue? Because they are all together 19 points, right?
Exactly. They are all going to be blue. They are all going to be, so once your k gets high enough, if your k, for example, is larger than the actual number of points, then the color that those points are going to be selected into is just going to be the one that's the most dominant. And so in this picture, there are 10 blue dots and 9 red dots. And so if you look at the 19 nearest neighbors, you're always going to have more blues than reds. So every triangle will be blue. And that is analogous with overfitting, right? You are selecting too many data points to train on. And so this is the exact same type of error thing where you are decreasing bias, increasing variance. And if you have too large of a k for selecting your nearest neighbors, your model will not do a good job. So how do you choose the proper number for your k? Cross-validation, same as we picked for these kind of tuning parameters, right? So our lambdas, the thetas in the PCR, the number of variables in your stepwise selection, and now the number of k that you would choose for k nearest neighbor. Cross-validation, out-of-sample cross-validation is going to be the best for making sure that your predictors are doing a good job given whatever choice of k that you are making. Okay, so let's go on to implementation in R. Okay, it's gonna look, the setup is slightly different, but the syntax shouldn't be too hard to learn. So example of k nearest neighbors. So predicting across the range of prices and sales using the car seats.new, the one that contained all of the predictions. We're going to make a new set. So we've made the predictions for the Logit model. We've made the predictions for the LDA model. And now we're going to do the predictions for the KNN model. So this uses a function called KNN. You're going to train on car seats, price and sales. Oops, I didn't have a parentheses here. And then our test, which is it's not really training or testing anything as which is okay. This part I guess is a little bit confusing now thinking about the syntax. The training and testing just means your actual observations versus the ones that you're predicting on. So I would almost call the test in this case the predictions, not like an out of sample. I mean, it is out of sample, but in this case we're using it for just to do this comparison of the predictions. Price and sales. So CL stands for class. This is your outcome variable, and this is what we want. It's a vector of your outcome variables. And let's just say k equals 3. So we're going to look at the 3 nearest neighbors. Don't worry about the L, just you can always leave it at 0. So this runs this model, and then let's take a look at our ggplot. The dot's a little bit smaller. See what happens. Okay. Cool. So this plot is going to look substantially different from our multinomial logit regression predictions and the LDA predictions, right? You can imagine that this like procedure that we just did is quite different. And I could go point by point and just manually perform the KNN to confirm these results, right? So if let's see, if I were to go right here, my 3, okay. I am realizing something here. Okay, that's all right. Let's we'll discover this issue as I walk through this. You'll notice that okay, if I put a point right here, okay, the 3 closest points as seen in this graph are blue, and therefore it's blue. If I go here, you know, my 3 closest points are green, and so it's green, and so on. And you can kind of do this kind of procedure throughout, and you should find it to be sort of consistent. Now, you might, if you're looking really closely, you might find something a little bit odd. So I'm gonna pick this point like right here. Okay, the model's predicting blue, but to my eye, it looks like so this is a 3, so my nearest neighbors is k equals 3. So if I look at the 3 closest, it's blue, green, green. So why isn't this point green? And this is actually something that depending on the context, you may actually need to do correction here. So the reason why it's not green is because the axes are not the same, and it is treating the distance equally between sales and price. So you may actually want to normalize them against each other so that the ranges are the same. Or if you think that the weighting should be the way that they are, then you can leave it that way. But you can see because of this, the sales goes from 0 to 15, but price goes from 0 to like 200. Distances along the x-axis are, in theory, like way larger than the distances on the y-axis. And so I can try and emphasize that a little bit if I, this is kind of a ghetto way of showing this, but if I go like this, you know, at a certain point, if I go, it should, usually these things will replot. Actually, let me try that again. So let's replot this. No. Yeah. So suddenly you can see that that point that I chose over here, where it looked like these were the closest points, now now the closest point is actually down here, or at least it's closer. Maybe the graph actually needs to be squished a little bit more, but that is one of the sort of nuances that people often forget to do, as I have in this particular example, which is if it makes sense to do normalization, you know, make sure to do that. And with the ratio like this, it should be a lot closer. I'm kind of like eyeballing it. This is still, it still needs to be squashed down a lot more, but that is kind of how it goes for now. Okay, and how about now we can look at, okay, and then example across a range of different Ks. Okay, so I am just going to run the same thing here, but I'm going to put in a couple of different values of K so that we can see what happens as I change my K value. So instead of K equals 3, I'm just going to be K equals K from my for loop. And then we're going to save this. And we'll track of that. Okay, so run all this. And let's just quickly take a look at what this table looks like. Okay, so it's gonna look at a range of prices and sales. It's gonna tell you how many Ks you have, and then it's gonna do the classification, and it's gonna do that for all. It's gonna run 10 models where you have one neighbor all the way up to having 10 neighbors. And let's take a look at how these graphs will look like. Okay. Since there's so many points that it's plotting, it's not the sort of most efficient most efficient plot, unfortunately. And if this takes too long, I actually have it pre-plotted that I can just bring up so we can see. Oh, there it is. Right, and so let me make this a little bit wider. Typically what ends up happening is that as your value of K increases more and more, you will start to see a more dominant proportion of points becoming, so in this case, I'll just say it as an analogy, right? So the prediction, which is your background values, are becoming more and more blue because there are, of all of the points here, there are the most dominant points are blue in color. And so as I get my K closer and closer to the number of points, which is, I mean, in this case, we're not even close, right? There's definitely more than 10 data points here, but you will find that more and more of the plot will sort of fall into that value. Of course, it depends on sort of the local context of what points are around and how they're distributed. But generally, that's the pattern that you'll see. Okay, and so that is the sort of last classifier that we will talk about today. And so, yeah, you guys have a couple different tools at your disposal in thinking about classification methods for models where your outcome variable, your y, your response variable is discrete as opposed to continuous. And I think this particular method that we just talked about, the k nearest neighbors, is like fundamentally different in approach from the way that we have done the classification with the regression models. And we are going to start getting more and more into sort of this type of approach in thinking about predictive models, where we're starting to think, we're starting to branch farther and farther away from sort of classical inference techniques and more towards machine learning predictive techniques. Okay, great. So we'll end a little bit early here today. And in the meantime, again, I will stick around for any questions folks may be having about either the stuff that we talked about today. If anyone has been diligent enough to look at the homework that was just posted today, or about projects, happy to talk about any of those topics.